All right, class, let's begin. So first things first is we got to figure out what in this world is this C. We talked about it in the last class. Where does C come from? What does it mean? Anything like that. And then we'll move on with the rest of the lecture for 5.4. So let's jam. So what is C? And this is, let's just give a story back to Wednesday's class. Remember on page 392, I believe is the page number. It had, and we did it on the board, we had all these antiderivative with C values in them. Okay. So we'll talk about them. So let's go for it. Let's talk about what the C value is. So first of all, let's go to the example for it. Example for it is, let's take a derivative of x to the third over 3 plus 4. All right, so please go ahead and do so right now. Go for it. Take the derivative of x to the third power divided by 3 plus 4. So our derivative rule says we take the 3, put it down front, subtract 1 from the exponent, and then we have the 3 that was there already. And then what's the derivative of plus 4? It is a 0, right? Because constants are 0. And what happens to the 3's? They cancel. So in this case, we got ourselves x squared. Okay, are we good? So notice that if there's a constant here, the derivative of the constant will always be 0. But what happens if it's a different constant? What happens if this was x to the third power of 3 plus 12? What happens here? All right, so let's see. Take the derivative of that, and I think you guys already see it already. That little 12 is also going to go to 0. So hold on. So when I take derivative, all constants go to 0. And look at that. Hold on. I have two derivatives that are exactly the same, but they don't come from the same exact function because of the sign change. And think about this here. Remember what are the derivatives calculating? They're calculating slope. All right, so if I'm just 4 units higher, or I'm 12 units higher, does my slope change? Not at all, right? Not at all. The constant change in a formula or a graph does not change the slope. Okay, so now here it is. What happens if we go the other way? Okay, so you should notice something missing from what we've been doing before. Notice their numbers are gone. There are no numbers over here. So when I take the antiderivative of x squared, which I think you guys all know what that would be, but if there's no numbers here, here's what's happening. I want to take a formula, and at the end of it, I also want to have a formula. So let's take a look at this slide together here. So let's see. How do I take the antiderivative of x squared? I add 1 to the exponent, x3, divided by 3. And then I have to put a plus c because I don't know. There was possibly some kind of variable here. I'm sorry, some kind of constant here, because when I took the derivative of it, it disappeared. So there it is. We're accounting for that constant that could have been there. Now, this guy's called the indefinite. Write these down in notes, please. This is called the indefinite integral. And it means this. The indefinite integral means there are no numbers here. And we go from an indefinite integral into a formula. We good? There it is. An indefinite integral gives us some kind of formula. And here's our formula, x to the third over 3 plus c. Whereas if I did add something like this, again, same exact formula. Let's take the antiderivative of this. Okay, so how do we call this? We call this the definite integral. So we just exclude the in. And I did not write it in here. If you want to write it on the bottom here, go for it. Just put definite integral. A definite integral has a starting point and an ending point, and the answer is just going to be a single number. Good. Definite integral has a starting point, ending point, and is going to have just a number as the final answer. An indefinite integral does not have a starting and ending point. It goes from an antiderivative to a function. There it is. Okay, so let's do this one here. It's going to be pretty easy. So if we add 1 to the exponent, divide by that exponent, evaluate this from -1 to 5, what we're going to get is plug it in. So this is 5 to the third over 3 minus, in parentheses, I like to do parentheses, minus. This is going to be, oh, you know, we have to also put a parenthesis right here because we're going to take powers of negative numbers. Okay. Let's see what we got here, though. 5 times 5 times 5 is 125 over 3. This is going to be -1 times -1 times -1, which is still -1. Subtracting a -1 is adding a 1, so it's +1 over 3. And we get ourselves 126 over 3, which is 42. Okay, so there's what I want you guys to notice. Indefinite integrals, we're going to go from indefinite integral to a formula. Definite integrals that have starting point and ending point of a final answer of just a single number. Okay, so then the question is this. If this is the more generic form right here, right, where does this C, how does this C disappear when we take the definite integral? So we should probably see this, what happens here to these C values. So let's do this here. Let's do this all over again. But this time, we're actually going to include the C values part of our answer, which means, hey, an antiderivative, when I take it, I know there's going to be some kind of constant here. Could be 0, could be 3, could be 12, could be a 4, could be -99. I don't know. So let's do this one. Let's do this exact same problem. And now adding in the C values and seeing what happens. All right, -1 to 5, x squared dx. Let's go with it here. Again, this is not the way we're going to do these. We're going to do some example problems in just a little bit here, but I want you guys just to understand the fact that if you have endpoints, you're going to end with a single number. No endpoint, no starting point, you're going to end up with a formula. That has C inside it. Okay, antiderivative of x squared is x to the third over 3. Oh, that is not good because I messed it up. Okay, class, sorry, forget it. Why did I? This should be. Let me just. Not my fault here. This should be x to the third over 3. I have the answer right down here. So notice what it is, x to the third over 3 plus c. I'm going to include the c in here and just see what happens with the c. I plug in a 5 into here. This is 5 to the third power of 3 plus c. That's the endpoint. Subtract from the beginning point, which is -1 to the third power of 3 plus c. That's what I got to subtract. This is 5 times 5 times 5 is 125 over plus c. That's the first part. And then this one's going to be like this. It's going to be -1 times -1 times -1. This will be a -1. And then this guy gets multiplied in. So 1 times -1 is a positive 1/3. And 1 times a positive c will be a minus c. Okay, and this is what happens. This is what happens to the c's. They will disappear on you all the time. That's why c's don't ever show up on definite integrals, because eventually they'll just cancel themselves out. So we don't need to include them when we do definite integrals. So let's finish it up. 125 over 3 plus 1/3 makes 126 over 3. Divided into that gets you 42, which we found last time. Okay, hopefully that makes sense. So there it is. Indefinite integrals, you have C values. Definite integrals, don't need it. It's extra information that eventually gets canceled out, so we don't even include it as our answers. Okay, just want to touch base. That is what the C is all about. Now let's go with it here. I'll give you guys a little time here. So let's talk about 5.4. This is called the indefinite integrals. Oh, hold on. We're going to have C values here. Is that right? And the net change theorem. So we'll talk about what that means. And we already know it. I could tell you it right now. It's if anything is above the x-axis, it's positive. Anything below the x-axis is negative. That's it. We'll do a little thing on it. Okay, hopefully that's enough time to write that stuff down. Let's jam. So exercise number 1. Now these ones are going to be a little bit more difficult to calculate. Gotta think things through when we do this sort of easy one though. And you know what, let's do this here. I'll give you guys about 30 seconds. Try this yourself, go for it. So the first thing that comes to mind, question is this a definite integral or indefinite integral? I'm gonna go 0 to 3. This is a definite integral, okay? So I'm gonna take the antiderivative of this and then evaluate from 3 to 0. I don't need the c value here. All right, 30 seconds, go for it. Let you start it. All right, let me try myself here. So this is going to be x to the third. So that means I need to add 1 more to the exponent. Divide by that exponent. Minus, that's a 6. I'm going to add 1 more to the exponent. So this is a 1 technically. So it's going to be 2 over 2. And that plus, again, just to show you that the c is going to cancel off any time whatsoever. Evaluating from 0 to 3. Sometimes some textbooks write it like this. Sometimes they put a bar line. Sometimes they have a bracket around the front. You'll see it different text books will have it differently. And then just going to introduce you to each of the terms here. So in this one, I'm just going to use this as their bracket. Evaluation from 0 to 3. So let's plug in a 3 in here. 3 to the 4th power. You know, let's simplify this just a little bit more. I think I like that a little bit better. So 6 divided by 2 is just a 3. Again, do you need to include the c in here? No, you don't. You can skip this step entirely. I think we covered it in the last example already. So I want to show you that no matter what we're evaluating, you're still going to have opposite c values. So plugging in a 3 to the 4th over 4, minus 3 times 3 to the 2nd, plus c, all that. And then there'll be a subtraction. Plugging in a 0. I like that. I like plugging in zeros. Notice I don't plug in 0 for the c value, right? So notice, yep, here it is. This is 81 over 4. This is 27, looks like, yeah. Plus c. And everything on this side is going to be 0, 0, 0, except for another c over here, which is subtract. Again, c's are gone, right? Don't need the c value to finish it off. But we do need common denominators. So let's go with it here. I'm running out of room. Let's try it. 81 over 4 minus, make that into a 4. That should give us 108. And how about a negative 27 divided by 4? Oof. Okay, I think I stopped there. All right, so that is the evaluation process. Don't need c values anymore when we do definite integrals. Okay, something we touched on last time, but I want to go through this one as well. So I think we talked about this on page 392. Here are some properties just for us to keep in mind. If you have a constant and you take the antiderivative, you can move this constant out to the front, and then you can just deal with just the function only. That's one rule, one main rule. The second one, under subtraction as well as addition, or addition and subtraction, we can split off these antiderivatives. Next, if there's a constant called k, the antiderivative is kx plus c. Right, so again, there's no beginning nor end. This one this is not any mark. I just want to tell you that there's nothing here. That's all that means. All right, so if we're going to write these out, normally in calculus, we write it out with the indefinite or non-values for stop and start. Okay, then next, we did this last time here, but just to reiterate, we take the derivative of sine, it becomes cosine. Therefore, we know that the antiderivative of cosine is going to be sine plus c, right? Because we don't know if that had a constant or not. All right, so derivative of secant is secant times tangent. Therefore, the antiderivative of secant times tangent is going to be secant plus c. So this is all works from the exact opposite way of getting the derivative. So yes, notice we mentioned last time, we don't have any derivatives from chapter 3 to give us tangent. Therefore, we do not know the antiderivative of tangent. Now, of course, in higher mathematics and calculus, later on, yes, you will learn what is the antiderivative of tangent. Okay, let's jam. So let's put up some examples here. Let you guys maybe like 2 minutes to try it yourself here. I'm going to do, I'll evaluate the integrals. Here it is from 0 to 2 of this function right here. And all yours. Well, of course, I'm going to put something fun in here. All right, and you should say to yourself, you know, first one's easy, second one's easy, this part is tough. So what I do, well, here's what you can't do. Notice you have 2 different terms on the bottom. You have an x squared plus 1. You cannot split those off. That's not to say you can't split off denominators if there's 2 terms. So now we have to think about what function, if I take the derivative of it, will give me that as my derivative. Crazy stuff. Let's go for it here. So tell me if you agree. First one's going to be this right here. We add 1 to the exponent and divide by that exponent. Same thing here. We add 1 to the exponent makes 2, divided by the exponent. And the fun begins. So first things first, this 3 is a multiplier. I can take that out just kind of in my mind. I'm going to stick it out in front. So now there's a 1 right here. So thumb through your book, especially for your derivatives. Thumb through your book for derivatives. Find out, is there anything here that if you look at it, take the derivative of it, wind up with 1 over x squared plus 1. So let's move the 3 out in front. Pretend there's a 1 there. Look at your derivative list. Anything that finishes off with 1 over x squared plus 1. Yes. Tangent inverse. Oh boy. Tangent inverse. When you take the derivative of x, it becomes 1 over x squared plus 1. All right. This is a definite integral. So I'm just evaluating from 0 to 2. So plug in a 2 into all that. I'm going to subtract off by plugging a 0 into all that. Before we do that, I might as well just simplify stuff out. So 2 and 4, that makes nice. 6 divided by 2 is 3. And plus 3 tangent inverse of x. Whew, that's going to be tough. So 0 to 2. All right, all yours, go for it if you can stay ahead of me. All right, let's go with it. Plug it in a 2 into that. I went a little fast here. 2 into that makes 16. 16 divided by 2 is 8. 2 into that makes a 4 times 3 is 12. And let's see what begins with the rest of it here. So minus or sorry, plus 3 tangent of negative 2. I'm sorry, of 2. So that's the first part. Then we plug in zeros, though. These zeros are nice. Zeros all plugged in. The one thing is, what is the tangent inverse of 0? All right. So if you take tangent inverse of 0, which is right here, right? Oh, that's interesting. So this would be 1 over 0. This is the y coordinate and the x coordinate. So the question is, which radian measurement makes that true? Oh, it's 0. That's right. So theta tangent of y over x makes tangent inverse of 1 over 0, and the angle measurement that makes that true is 0. It's this guy right here. So, okay, so I got this here. I think I got -4 plus 3. Now, this one I don't know. I don't know the exact value of tangent of 2. If this was 1, I would know that, but not 2. And if you want to use your calculator at this point to simplify what that would be a -0.678. All right, next. Okay, you can add extra lines in there. That's fine too. All right, so the net theorem property, let's talk about this here. We know this already here. Just means this: if you go from 0 to 2, you're going to have some area that is above the x-axis, and then you have some area that's below the x-axis. And all we got to think about is this: the fact that anything of the above x-axis is positive, anything below is negative. So anything below the x-axis has to be subtracting from the full entire area. So yes, that is why we have a negative area. Thought that was not possible. Well, yep, it is possible if you're just looking at area above the x-axis. And if you have a negative, it just means you have more area below the x-axis than above it. That's what the net change theorem is all about. All right, but let's do some practice here. B, all yours here. All right, give you a minute-ish. Ooh, this should be fun. All right, give you a minute to start. Go. All right, give you a hint, the fact that we only have one term in our denominator. If you only have one term in your denominator, what can you do? Now you can split them off. So that t squared goes under that one. This one's going to be a fun one. That goes underneath that. And this goes underneath that. Cool, cool. And let's simplify, see what we got. So from 1 to 9, that's a 2. That is going to be just a square root of t, right? The t to the seconds cancel. But isn't square root really just t to the 1/2? And then we don't like to deal with fractions if we don't have to. So anything that we can bring up to the top, we do. So t to the 2 in our denominator becomes t to the -2 in the numerator. Ooh, okay, go for it. See if you guys can undo that. All right, let's go with it here. So if I have a 2, I'm going to get a 2t. I'm going to add in a variable now. Oh, that's a little rule number 3 that we had on sometime previous slide. If I have t to the 1/2, if I add 1 to the exponent, it gets me 3/2. If I take that to the bottom, I take 3/2 to the bottom, it's going to be 3 over 2. But it's going to be a fraction. It's going to be a complex fraction on the bottom. So what I do is I just flip it over in my mind. So 2 on top, 3 on the bottom. Hopefully that helps there. And now I got the last one. T to the -2 originally. So t to the -1 over -1. Evaluated from 1 to 9. Okay, anything to simplify? Yeah, we could simplify that over there. Okay, guess I can simplify that. All right, what's the thing that I'm missing here? This should be still to the third power. Let's see if I corrected it later, but it should be like that, right? It's the square root of t, but to the third power. All right, let's keep on jamming. So 9 goes into there. Oh, there it is. Now I put it in. So I can put the 3 there on top there, or I could put the 3 inside there. It doesn't matter whichever way it goes. That's fine too. So 3 into here. In fact, it's almost better when you do the work for it. Let me do it this way here. It's almost better to go like this. So the question is, as 9 gets in there, square root of 9 is 3. The square root of 9 is 3. But then 3 times 3 times 3, it's going to be 27. 27 times 2 is 54. Ooh, I think I might have made a mistake here. Let's go with it here. So we got 54. 3 goes into 8. The 3 goes into 5 once. 2 left over. 18. Okay, yeah, I was right the first time. Okay, just want to make sure. Okay, and then 9 goes in here, which makes a 1/9. Subtract, putting in a 1 into all that. So 2 times 1. 1 into all that makes a 2/3. 1 and all that makes a 1. Okay, all yours to finish off. Go for it. If you have not done so already. That's going to be 36. 18 plus 18. This is going to be 3 right here. Plus 2/3. Okay, I've simplified that at least. So for my fractions, I probably need a common denominator of 9. And the rest I can do by myself. So let's get rid of parentheses now. So move this little negative into there. So I still have a 36 plus 1/9. Negative goes here, which is -3. Negative goes there, which is a negative 2/3. All right, keep on going. And since we're going to have a common denominator of 9, you might as well just do it for all of them. So for the first one, let me go back real quick on the slide. Oof, 9 is a common denominator. It'd be 9 times 36. This would be 9 times 3. This would be just an extra added 3. So then let's go for it here. So 9 times 36 would be 324. Second 9 just stays. Third 9 is a 27. And the fourth 9 is just a -6. All right. Once we have everything else in terms of common denominators, 324 plus 1 is 325. Subtract 27. Subtract 6, and it gets us 292 over 9. And now the question is, does 9 go into 292? I don't think so. It goes 32 times with a little left over. All right. And I'm thinking this right here, or I'm thinking this right here. So either one just going to work just fine. All right. And next. All right, now find the general indefinite integral of this one. Ooh, indefinite means no start, no end. Therefore, we're going to have a C value, but we don't have to evaluate it. We just produce the function, and that's it. So here it is. This was a fun one. Here it is, cosine theta over sine squared theta, d theta. Oof. All right, again, 2 minutes. Try your hand at this, see what you guys get to. All right. Let's see. Now it's been about 2 minutes here. Hopefully talk to the person next to you and thought through this here. So how in the world do I take an antiderivative cosine over sine squared? Hold on. Got this idea in my head. So I can divide the bottom out into two different multipliers. So if it's a sine squared on the bottom, I know it's sine times sine. If I have a cosine on top, I know cosine is only over one of them. That is it. So there's kind of like these little small tricky math stuff you have to do a little bit of. All right, what is 1 over sine? I think that's cosecant. And what is cosine over sine? Cotangent. And the question is this, do we have any formula that takes us from cosecant, cotangent backwards? So it's, yes, we do. It is negative cosecant theta, and we'll put a plus c there. All right, class, hopefully that was good enough of a good start for 5.4, and enjoy the rest of your day.